So we have just finished calculating our CL2D analysis. So we may go directly to, let's analyze the classes first. So we see these classes here. So this is a summary of the data that we have in our dataset. So if you go over each one of the images, you see the number of images. 43 experimental images have been assigned to this class, 48, 51. You may also, for instance, display labels shows this information. So here you have the summary, and in fact, metadata are rather rich files that has a lot of may have a lot of information. So for instance, here you can see the classes, but you can also see the info. So the info gives it is a structure in blocks, so there are different blocks inside the metadata. So this is the block of classes, this is the block of information, this is the block of images assigned to class 1, etc. So in the info we have some information about how the algorithm was proceeding. So for instance, here we have for the last iteration, so we have the 4 iterations when it was refining with 8 classes, and how the CL2D similarities, it is correlation or correntropy. You may read the paper to see what everything means. So how the correntropy or the correlation was increasing, and how many images were changing the class from one class to the other. So you may also see which are the images assigned to class 1. So here you have the full image information, or you may see simply the gallery of images. And you may also see the classes sorted. So the classes sorted, they are rather useful. Let me remove the labels. So the classes sorted, in this case it doesn't make sense, but in other asymmetric particles, the classes are sorted by similarity. So the most similar particles are so the most similar classes are close to each other, so you can see the different projection directions, if there are subtle differences among them, etc. So here you have all the classes. So all these classes in principle are good. Sometimes when you have an automatic picking that did a bad job, you will see some classes that have mostly garbage. Also, you may have classes representing damaged particles or broken particles or contaminants, etc. So now you would choose the particles that you like. So in this example, we like all the images, and then you right click and you say save images, and it will tell you you are about to save 356 images from 8 classes. Okay, so, and we are saving it in here, so we'll explore a little bit more this structure. So we save them, and we have now saved the metadata with the images behind these classes. Okay, so what are the possibilities that we have here? So let's say that I want to see the images assigned to this class. So you have one possibility. You right click on the class, open images. So now you have all the 43 images assigned to that image. If you compute, for instance, the average and the standard deviation, you will have the same average, and the standard deviation is just the standard deviation of all those images. Something that is very useful when you analyze 2D data is to compute the power, the principal component analysis. So this principal component analysis constructs a basis in which these images are well expressed. So for instance, here we see a little bit of structure, meaning that there is a little bit of mixture in this class. This class should be further divided into more classes, but already we have only 43 images assigned to this class, so if we further divide, we will have even less. If you don't see any structure, like in here, mostly this is noise, so that means that you don't have an heterogeneous population in this class. So ideally, when you do the PCA analysis of the images assigned to a class, you should see all the images like this one. So it is mostly noise. Also, you may explore what is the Fourier shell correlation of this class. So you compute the Fourier shell correlation of the class. It seems we have some problem in here. So okay, so for the moment we forget about it. And you may also, for instance, here it is mostly the analysis that you can do. So we now at this point you may discard those images you don't like, the experimental images that you don't like. So this is a kind of cleaning step. So you choose the images you like, and you may go to further analysis. So for instance, you may with the images you have saved, you can do an ML2D with fewer classes. For instance, ML2D is very useful when you choose images that are subtly, or classes that are very similar to each other. So you take all the images that have been assigned to those classes, and then you further analyze with a different algorithm. A different algorithm can be ML2D, or since they have been aligned, you can use Kerdensson, rotational spectra, and these screen classes and the noise particles. We will see them in a separate tutorial. Okay, so also only align is a CL2D, but with only one class. So sometimes it is useful to take all the extracted images to align them, and then you perform another kind of analysis. Okay, so we were here at this CL2D, and we had computed core and the stable cores. So let's see what is the core. So if you look at the core, in fact they look very similar to the standard classes, maybe a little bit noisier, and the reason is that we have removed images from the classes to construct the class core. So we have removed those images that we don't trust automatically, and this rejection is related to the parameters that you saw in the CL2D form. So we have rejected some particles automatically. So for instance, here we had 18 images. Here you have in the corresponding image, you have 18 images to 51. So for instance, here we have rejected one particle that we don't trust so much. So you have the core and the stable core, that is a further refinement. And again, here you have lost more particles. Okay, so in this data set it is pretty clean. So we can rely on the standard classes. Okay, so some other analysis that we can do. Remind that this algorithm is iterative. So we don't want to see the last level. So it is the images have been calculated or have been split into first into 2 classes, then into 4, then into 8. So we refer to these splits as levels. So into 2 classes is level 0, then level 1, into 4 classes, level 2, into 8 classes. So let's say that we want to analyze the level 0. So the level 0, now we see the 2 classes that have been calculated. This one with 300 images, this one with only 40. So let's say that we want to analyze the images that are behind these 300 ones. Now we do a PCA, and we clearly see a lot of structure. So we see that the main differences among the images are related to the capsid of the virus. And this is the main difference. This is the second most important difference. It is here. The third most, we see differences between the internal part of the capsid. So we see a lot of structure. So all this structure is meaning that you should further subdivide the classes. Okay, so you may explore the images at the level 0, at level 1, etc. So these are when the images were split into 4, etc. Okay, so now we have a summary of our data that we like, and then it is time to go into 3D. So to go to 3D, we first need an initial model. There are several possibilities. So if you have performed random conical tilt in the microscope, then you may analyze it here. And the input to the random conical tilt, normally it is a 2D classification metadata. So you go here with the classes computed either from CL2D or ML2D, and you may use classes, class cores, stable cores, or the classes at different levels, so level 0, level 1, level 2, whatever. And then you would have to say which classes to reconstruct, but this will be done in a separate tutorial. Okay, so another possibility is to convert a PDB that you have of your own. So let's say that you have a PDB that is related to your structure. So you may take the PDB and produce a voxel volume out of that PDB at the right sampling rate. And the possibility that we will explore in this tutorial is Transact. Simulated annealing is somehow related to Transact, but it can be combined with Transact, in fact. So it is much slower than Transact. Normally Transact gives very good results in fast time, and simulated annealing is just in case that Transact fails, you may try to use this simulated annealing. Okay, so what is Transact? So Transact, what it does, it takes a set of classes, so let's say our classes, and you may use these eyes to visualize, to check that you have chosen the right file, and then you provide some information that you have about. For instance, we know we are reconstructing viruses, and these viruses, it has some symmetry. For instance, there is a standard nomenclature that you have in this link. You have how to represent different kind of symmetries. If you don't have any symmetry, just give C1. And so we will impose an I1 icosahedral symmetry to these viruses here, to these virus classes here. And this initial volume is a way of biasing the Transact algorithm. So if you have a previous idea, for instance, you may have you have a particle that is mostly symmetric, but it is not truly symmetric. So you may give here in initial volume, you may give the symmetric particle, so that you bias a little bit the assignment, the angular assignment, but then you are reconstructing with a C1 symmetry, so that it can break the symmetry of your input volume. So let's keep it as I1, and most of the time you don't need here an initial volume. Then the sampling rate, in this case it is 6.5. Then it is important to modify some parameters here. So if you keep the sampling rate to 1, this parameter you may not need to change it, and otherwise if you change the sampling rate, you have to say what is the maximum frequency or maximum resolution of the volume you want to reconstruct. So let's say we want to construct a volume that is valid up to 40 angstroms, and then here we have the important Transact parameters. Normally, if you have many classes, you don't need to touch them, but if you have very few classes, then it might be important to touch these parameters, because otherwise it may not work. Okay, so what is Transact? Transact takes all your classes, now it takes a subset of your classes. So let's say you had 300 classes. This is not our case. We have only 8. But let's say for the example that we have 300 classes. So it will take a small number of them. So a small number of them is 3 times 3. So 9 classes out of your 300. To choose wisely these 9 classes, it performs a dimensionality reduction. So it projects your classes into the 2D plane, and then in this 2D plane it constructs a map of a grid of 3 times 3, and then it takes a sample from this map. But then, since we have so few classes, we cannot perform this dimensionality reduction. In fact, we have only 8 classes, and we cannot take 9 images out of 8 classes. So we don't want to perform a dimensionality reduction, and then it asks you how many samples, how many classes you want for your random subsets. So we will use just 4. Okay, so it takes these 4 images, these 4 classes, it assigns random Euler angles, and it constructs a volume out of it. So most of and it repeats this many times. In this case, by default, it is 380. There's some theoretical justification for this funny number. If your particle is easy, you may perform many less iterations. So you assign randomly Euler angles to 4 classes, and you repeat this 40 times. Okay, so now you have your random volume. Your random volume, most of the times, it will be very bad. Then, how do you evaluate whether your volume is bad or good? Okay, so you compare your volume to the rest of the images, to the rest of the classes that were in the classification. So for instance, we had 8 classes, we have chosen 4 randomly. So there are 4 other classes that have not been chosen. So we compare these 4 other classes to the volume, and we compute whether what is the correlation coefficient. So if the correlation coefficient is high, we say that other class is an inlier of that volume. If it is low, then it is an outlier of the volume. Okay, so what is the threshold of correlation to decide whether it is an inlier or outlier? So by default it is this value. We have observed that most of the time you don't need to touch it, but since you have so few particles or so few classes in this example, we will lower the number to consider the threshold to consider whether it is an inlier or not. Okay, so out of these 40 volumes, most of them will be wrong. We think that the best 5 have some chances of being good, and we will do a projection matching with 5 iterations for these 5. Okay, so these are the Transact parameters. For instance, in this case, you may choose that all the classes that you have in your classification participate in this refinement. So we can click this button to yes. So if you have this is we can use this option because we know that we have an homogeneous population. If you think you have an heterogeneous population, then normally you would prefer to not to use all the images, because through the inlier threshold the algorithm can leave out some classes that do not correspond to your structure. Okay, so we'll use all of them. Then we launch this. Okay, so now it is making all these random subsets, constructing for each random subset a volume and comparing it with the rest of the classes in your classification, and then for the best 5 it will compute, it will refine those volumes. This is a relatively fast algorithm, so just in a few minutes, couple of minutes, you would have your structure. So now we have our volumes. So we go to the list of volumes, and these are the different volumes that have been constructed. So if we go through all of them, we see that most of them are the same. They are just simple rotations of one and another. So let's take any one of them. Let's say the first one, and in this view, in the metadata view, you have some important information that may help you to choose the volume. So these are the different volumes, and there are 4 different parameters. So the 4 different parameters try to qualify the volume, how good it is. Okay, so we see that all of them are more or less the same. So in this case, we cannot discriminate because all of them are good, in fact. And what is the meaning of those? Okay, so this is the sum of all the correlations of the inliers of this volume. So there are classes, 8 classes. These 8 classes have an average correlation of 0.93, and if you multiply 0.93 times 8, you get 7.4. So this is the sum of all the inliers. So the correlations of all inliers. Then do you remind that we set a threshold for the being an inlier or not? So if you take the correlation, you subtract the threshold, and then you sum all of those values, then you would have this 3.4. And then you may think that a volume is as good as the worst image assigned to it is. Okay, so you take the worst inlier and you look what is the cross correlation of the worst inlier. So the worst inlier for all volumes had a cross correlation of 0.89. That is pretty high. Okay, so let's say we want to see one of these volumes. So let's say just the first one, and we can open it with Chimera. So now we are opening it with Chimera. So we have here. So we have the volume we have reconstructed at 40 angstroms, and this is a projection of that volume in that direction. Okay, so it doesn't have precise. Okay, so if you change your point of view, this projection is updated, so you can try to figure out how the different projections look like. Okay, so one typical step at this point is to compare the classes with the volume, just to check whether the volume is good or not. Okay, so we go to the classification part and we do the screen classes. Okay, so in the screen classes, what you have is you have a set of classes, let's say those classes there. Now you want to compare to this proposed volume number 0. It has a symmetry I1, and now it is comparing the classes with respect to the volume. Okay, so this was pretty fast, and here we have the same 3D representation. Okay, so it is simply the same thing, and it changed the projection. And here we have this table. Okay, so what is this table? So this table has the class that you have computed in the CL2D, the corresponding projection from the volume that you are comparing it to. So you can see this thing here corresponds to this thing in the volume, this capsomer here corresponds to this one, here the capsid looks like this, etc. And then this is the difference image. So you can see what are the differences between this and this. this table is sorted by maximum cross correlation. So the maximum cross correlation here is this 0.87, and then it goes down to 0.75. So the worst classes are at the end of the list, and you may decide, oh, this class does not correspond to this volume actually. Here are the alignment parameters. So these parameters here define from where you are looking at the volume. So this class corresponds to a view that is seen from these Euler angles. And interestingly, here you have the tilt angle. The tilt angle is normally rather important for identifying the projection direction. And here you have the different shifts, whether you had to shift or not the class to align it with the projection of the volume, whether you had to flip it or not, how many images were assigned to that class, and then this Fourier ring correlation of the class, differential phase residual. These two are numbers describing how good the classes are, and the scale factor. Okay, so here let's say that we like all those, let's put it smaller. So we like these classes and we don't like these ones. In this case it is not the case, but just for the sake of illustration. So we may now right click and say save the images assigned to those classes, save them as a separate metadata, so that I can further analyze this metadata and analyze them in 3D. Okay, so this is not the case in this example, so we simply are happy with all those classes, and we see that they are consistent with the volume we have constructed. Okay, so we are happy with that volume. So the next step normally is to go into projection matching. Okay, so the projection matching, what it does is you take some input images, for instance the images that we selected at the level of 2D, or the images that you have selected at the level of these screen classes, comparing a set of classes with the 3D volume. And so you take those images and then you take your volume, so volume proposed number 0, and you have to specify the parameters for the refinement of that volume. Okay, so if you want to do a CTF correction, this is amplitude correction, because the phase correction we did at the when we extracted the particles. Then you would leave this section on, and what you are defining here is how to group the particles according to having similar CTF groups. So you're making groups of CTF, so all the particles that have similar CTF, they go into the same group. And you can be rather tolerant and putting many micrographs together in the same group, and then you put larger values here. Or you may be too very strict and just making a group per micrograph. So it depends on you how much you want to go into this amplitude correction. And what we do here is a Wiener filter correction in 3D. Okay, so since we lost a lot of information when we extracted, because we were doing a downsampling by a factor 5, we will not do the CTF correction. And then you may mask your reference volume from one iteration to the next. So what we'll do, this projection matching is an iterative algorithm. So it starts with a volume. This volume is the one provided by Transact. It compares it to the images that you have in your set, in your data set, and then assigns angles to those images and update your reference, update your volume with those angles. So you make a 3D reconstruction of those images with those angles to have a better estimate of what your volume looks like. So now you have a better volume, and you can repeat the process of aligning the images to that reference volume, assigning angles, updating the reference, etc. So when you go from one iteration to the next, you may filter your volume, or you may mask it to make sure that you remove those features that are not related to your particle. For instance, in single particles it is custom to apply a mask so that everything in the corners of the volume disappear, or you may even apply a tighter mask if you want, and you can put it as tight as you like to your structure. So let's keep it as the maximum spherical mask that we can construct. So this is the for going from one iteration to the next, so that we remove every feature that is in the corners. Then you may also choose where to compare the images to align. So for instance, we may compare for viruses, it is rather common, the interior may be filled with RNA, DNA that doesn't follow the icosahedral symmetry, so you may leave the interior out and then align the particles only using a region of those particles, or you may keep the full particle or whatever. So in this example, since it is a virus, we will align only using the capsid. Okay, so now how you will compare your images. So you have experimental images, they are compared to the reprojections of your volume. So in the 4 iterations, in the first iteration, the volume will be projected every 7 degrees and be compared to the experimental images that you have. Then in the second iteration, it will be projected every 5 degrees, then every 3 degrees, every 2 degrees. So the angular sampling becomes finer and finer. Then how much can the images move from one assignment to the next? Okay, so in the first assignment, the first iteration, they are freely to take any value, so any angular value that they like. But then in the second iteration, they can move only 10 degrees away from the assignment in the first one. And then in the third iteration, they can move only 4 degrees away from the previous one. So these are parameters that force the algorithm to converge. They're not necessary, so many times it converges even if you say 1000, 1000, 1000, 1000. So you leave them all the time to choose freely the position that they like. But they are also used because they help to speed up the calculations. So if you know that you are very close to a local minimum, so your structure is good from the beginning, so you may leave these parameters as they are, so that you go quicker to the local minimum. If you are not so sure about your structure, then you would prefer a global optimization, so you would leave the angular search free for all the iterations. For instance, let's say that we want to do a free global search, so we leave 1000. If we don't give more parameters in here in this list, the last parameter will be repeated, so it will be 1000 all the time. Then you can say the same about the shift. So at the beginning they are freely to shift anything, and then in the next iteration they can only shift 10 pixels away from the previous one, then 5 pixels away, 5, 5, 5, 5. Then when you want to align an image to a volume, you have to look for 5 parameters, 2 shifts and 3 Euler angles. So this is a 5D search. So for the 5D search, it is a kind of global search, but it takes longer. So if you are close to if you are pretty sure about the shifts that you have in your particles, so you know they are not too shifted, then you may perform a 3D plus 2D search. It is suboptimal, but it is much faster. So again, if you want to keep it global, you keep the 5D search. If you want to do it local, you do 3D plus 2D. So how to say that? Okay, so let's say that for the first 4 iterations, we want to do a 5D search by moving plus minus 5 pixels. Then from the 5th iteration that we are not doing, in this example we are just doing 4 iterations, we don't want to do any 5D search, so you keep it to 0. So if you say 0 here, you are meaning don't do a 5D search, just do a 3D plus 2D search. Then what is the symmetry group? In our case it is I1, icosahedral 1. Then you may discard images. So by default we don't discard images, but you may discard images whose cross-correlation value is below this threshold, or you may discard the 10% of images with the smaller cross-correlation values. But there are some projection directions that systematically they have lower their cross-correlation values, so it is a little bit unfair to discard the 10% of images with a smaller cross-correlation, because probably you are discarding completely one direction. So you may apply the same policy but by projection direction. So for every projection direction you discard 10% of the images. So let's say we don't want to discard. You may also want to look for a small scale changes. So if you have a small magnification changes, you may look for these variations, and then you have to choose what is the 3D reconstruction algorithm that you want to use. Normally Fourier is the default choice, so it is pretty fast and it gives very good reconstructions, especially if you have a good angular coverage and you have enough particles. Enough particles is anything more than 200s or 300s. So if you have very few particles, you may want to use ART. And weighted back projection, ART is very good, but it is rather slow. So normally you don't use it if you have many particles. And weighted back projection is an algorithm that you use when you cannot use Fourier. And this is, for instance, when you have huge particles. Let's say you have viruses of 1000 cube voxels, and Fourier requires is memory demanding. So if you don't have enough memory in your computer, then you may use weighted back projection as a substitute of Fourier. So normally you use Fourier. So for the first iteration we will reconstruct only one half of the spectrum. So we don't reconstruct full spectrum, because probably at high frequency you have only noise and you have very bad alignment at the beginning, so you don't want to overfit that part. Normally you always want to compute the resolution of your structure, so we compute the Fourier shell correlation of your structure. And when you go from one iteration to the next, there are two important decisions that you have to take. So whether to low pass filter the reference, so when you align your particles in your next iteration, in the same way that you have removed features that you know that in real space are not there by putting a mask, so you have put a mask to remove the corners of the volume, you may low pass filter the reference. So you may say, beyond this frequency I don't want to align, so that you avoid overfitting. So this frequency to decide what not to fit, so how to low pass filter your volume, is decided based on the Fourier shell correlation. This is what you are saying here. So here you decide whether to filter or not, here whether to use the Fourier shell correlation or not. So normally we suggest to use the Fourier shell correlation and a little bit more. So a little bit more is Fourier shell correlation plus 0.05. This is in normalized units, frequency units. So the maximum frequency is 0.5. So 0.05 is 1/10 of the spectrum, of the Fourier spectrum. Let's say that you are very worried about your overfitting. So instead of adding a little bit more, you may subtract a little bit. So if you subtract a little bit, you are sure that you are trying to avoid this overfitting. If you don't have problems overfitting, yes, you may just keep the value by default. And then this is for alignment. What about reconstruction? So in reconstruction, in the first iteration, we just reconstructed one half of the spectrum. For the second iteration, we reconstruct whatever the Fourier shell correlation value that you have here, plus a little bit more. And a little bit more in this case is 0.1, that is 1/5 of the spectrum. Okay, so now we know how to fill this form, and we simply make the 3D reconstruction. So now it is computing. So we have finished computing the projection matching. Now we may go to analyze the results. So here we may see the results for iteration 1, 2, 3, and 4. So for instance, let's see how was the Fourier shell correlation progressing. So we see that this is the Fourier shell correlation of the first iteration, second one, third one, fourth one, etc. So what we see here is this is about 21 angstroms. In fact, if you remind, all the micrographs in this example, they have the first zero at 21 angstroms. So in fact, this is the first zero. So all of them have the zero there, so this is the zero what we see here. So we cannot recover the information at the zero. Normally this is done in a standard data set because you have a range of the foci, so not all of them, not all the micrographs have the same zeros. Okay, so it was progressing, so the Fourier shell correlation is increasing, except for this area where we don't have any information. Okay, so this went well. We may also look at how was the angular distribution changing over directions. So we have at the beginning, this is in the first iteration, this is an icosahedral symmetric particle, so we only need to assign angles in the asymmetric unit. So this was the initial distribution, and this is for iteration 2, this is for iteration 3, and this is for iteration 4. So what you see is that this coarse assignment at the beginning, that is mostly assigning in 10 directions, now it is much finer, and we are assigning in many more directions. Okay, so we have a good angular coverage, and now that we are sure how the process was going, we may analyze the volume. So we can see, for instance, the reconstructed volume. So the reconstructed volume is this one, and this one it looks good. These are the different slices. You may slice into different directions, and you may also look at it with Chimera. So for instance, here we have this structure that is about 21 angstroms in resolution, and again you have this projection direction. So this is the projection from the point of view of the observer. Okay, so that is looking in front of the screen. So this is the reconstruction of the virus at 21 angstroms. We cannot go further with this data set because we have downsampled by a factor 5. So if you downsample by a factor 2, for instance, you could go beyond this resolution. And also it is important to include different foci. But this is just an example, and we wanted just to give an idea of what can be done with Xmipp. Okay, so this is our volume. We may also explore other things, like for instance, we may explore the 3D angular distribution of the coverage of projection directions. So here it is the same structure, but now we have added this we have added these red points. These red points represent the different projection directions that have been assigned at least one projection, and here they are more or less the same, but the size of the sphere is related to the number of images that have been assigned to that direction. So for instance, they have been assigned more images to this one than to this other direction. So you see that the asymmetric unit here is rather well covered. There are a couple of missing regions, but normally this is not so important in this case. So you may also see how the shifts and the angles were changing from one iteration to the next. So for instance, here we are at iteration 4. So from iteration 3 to iteration 4, 10 images didn't change angle, then 20 images change 0.2, then 15 images change 0. Whatever. So you see that the maximum change, there were a couple of images or 1 or 2 images that change about 8 degrees, but otherwise most of them didn't change much in angles, and for the shifts it is the same. There was one of them that changed less than 1 pixel, and most of them didn't change at all, or it is just very small change. So this is about how the angles and shifts converge. You may also look at this plot here. This is every image, what is the direction that it has been assigned to. So this experimental image has been assigned to here, this experimental image to here, and they are aligned. So we don't see here very well, but there are some small details. For instance, these small details here, they correspond to the same small details in the reference projection. You may see what are the discarded images. In case you are discarding images, you may see which ones you have been discarding, and there are a number of analyses that you may do here. For instance, you may also see a B-factor corrected volume. So once you have your reconstruction, you may correct it by boosting the high frequencies according to the linear plot. So we have done here a fitting of how the linear plot looks like, and we have fitted it to a line and corrected by the slope of that line. So here we have enhanced the high frequency components, and you see more details. So for this example where we have downsampled so much, it doesn't make sense, but in a real example where you have full information, it makes a lot of sense. Then now you have your volumes, and the last step that you could do, and that we are considering in this tutorial, is the identify outliers. So in identify outliers, what you do is you take a set of images, for instance the ones that you have used to reconstruct your volume. You take the volume that you have used that you have obtained in the 3D reconstruction. So for instance, let's say this is the last volume, and now you compare these images to these volumes. This is just a question of whether you have corrected the amplitude of your volume or not, and we compare those images. Okay, so let's do the comparison. This is again relatively fast. You may see here how it is progressing. And what we do here is to compute the residuals of those images. So you take your experimental image, you take the the theoretical projection that corresponds to it, we compute the difference, and then we analyze that difference, and we analyze how normal that difference is with respect of the rest of the differences. So again, this is a measure of normality. It is not a measure of how good the particle is. It is assuming that most of your particles are correct, and a few, or a given percentage, but this percentage has to be smaller than 50%, are outliers. Okay, so now what we have here are all the images and experimental images and the reference that they have been assigned to, and also what is the difference, and we compute the covariance of that difference, and we can make some calculations on those covariances. Okay, so now they have been sorted by this set score. So the set score somehow shows how good they are. Oh, they have been sorted by, I don't remember now. But you may sort by any of those and decide, okay, all those, these are the worst images with respect to this set score. This now we may sort with respect to this one. So set scores around 3, they're pretty standard, and smaller set scores, larger set scores correspond to outliers. So normally 3 is a good cutoff point, and here it is the same. So the larger the set score, the worse it is. Okay, so this number, the less negative it is, the worse it is. So for instance, here we can see that there is some structure in the covariance matrix here, meaning that the covariance is not totally white noise or color noise with the same kind of color like the rest of the images here. So ideally you should not see any structure in this residual. This is the residual. This is the experimental image, and these are the residuals. You shouldn't see any structure in there. So let's say here that you identify outliers, and you say from this image to the end, I don't want them. So you discard your images. Now you would save as images good, and now you could again perform a 3D analysis only with those good images and so on. So this is all for this introductory tutorial. In some other tutorials we will see other possibilities that you have in Xmipp, but this is the most basic one. So how to go from the 2D micrographs to the 3D structure. If you have any problem, just you may write to xmipp@cmbs.csic.es. The web page is in here. So this is the main entry point, and here you have all the contact information and everything.